Thank you. Hi, we're talking today about how to scale Bitcoin. What do we want to do when we scale Bitcoin? We want lower latency, we want higher throughput, more bandwidth, more transactions per second, and we want security. How can we do that? We can try to tune the parameters. In all the plots here, I'll have time going from left to right, and these are blocks in rectangles. So what can we do? We can have larger blocks, and will give us better throughput. Seemingly, we can have shorter block intervals, and so we will get better latency. Transactions will come in quickly, faster onto the chain, and we'll have better throughput. But then we get forks when we do that, right? We have mining power loss. I'll talk about that. We have unfairness. Smaller miners get less revenue. This leads to centralization. I'll talk about that. We have a longer time to converge because of these forks. You don't know where you are on the chain. I'll talk about that. But the point here is the following. We need proper evaluation. We needed a scientific way to realize what we're achieving and how to evaluate which proposal is better, because we're seeing a lot of argument and we need a clear way to realize which way is best. Now, what we do in this project I'm presenting you is we run the actual code, the source, Bitcoin client compiled, that's it. And we emulate the world for it. We emulate the network based on measurements from the actual Bitcoin network. And we do some basic bootstrapping, and then we just run the raw code. So that's fine. Now we can, oh, I'm sorry, I should talk about scale. We have 500 machines. The experiments I'll show you later are from 1,000 Bitcoin nodes running on 150 machines with multi-core. So now we know how to run and how to evaluate, but what do we measure? So let's talk about measurements. The first measurement, and we'll introduce a couple of metrics here, a few metrics here. The first one is consensus delay. Okay? Consensus delay is how long it takes you to reach agreement. The easiest way to explain this is by example. The 80% consensus delay is 10 seconds if for 80%, at least 80% of the time, at least 80% of the nodes agree on what happened until 10 minutes ago. So we want a shorter consensus delay, and we agree closer to now. And these are the results. The first type of experiments we're doing are on latency. We want to reduce latency. We want transactions to come in faster. The bandwidth in all of these experiments is the same as Bitcoin's. So we reduce the interval between blocks, and we also reduce block size, so the bandwidth remains the same, but the blocks come in much faster. And you see on the X scale the block frequency. So 1 means 1 block every second, and 0.1 means 1 block every 10 seconds. We're running this at a very low scale because then it's very easy to see prominent results, but the trends are clear and they hold throughout. And so we see that as we increase the block frequency, the consensus delay improves. The Y scale here is also exponential, logarithmic, sorry. So we get improvement, which is what we want. But as we increase block size, and this is the second type of experiments I'll present, we have now a block every 10 seconds. Again, this is quite short. And we increase the block sizes that are generated every 10 seconds. And here you see that as you increase block size, you get the consensus delay way up, and it grows quickly. This is bad. So we're trying to improve bandwidth, and this is what happens to consensus delay. Second metric is called time to prune. This is a subjective metric. So as a participant in the system, I'm measuring the time it takes you to realize that you're sitting on a branch. So once you're sitting on a branch, how long it takes you to realize that the real chain is somewhere else. We obviously want this to be short. And again, we see an improvement here as we reduce the block interval, as we increase block generation frequency, we get better pruning time. And this will be the last optimistic slide for a while, so enjoy it. Block size, as we increase it, things go bad. We get worse and worse time to prune very quickly. Next, I'll talk about fairness, and we measure fairness as follows. We know that larger miners get more than, I'm not talking about any form of cheating, not selfish mining, nothing else. This is just blocks, miners mining, but larger miners, I mean any miner mines on their own branch if there is a fork. And so larger miners get more. So I'm asking myself, how much do the miners that are not the largest get? Do they get their fair share? And we want this to be 1. We want them to get exactly what they need. And we see that as we increase frequency, block frequency, again, bandwidth throughput is the same. We have faster blocks, smaller blocks. We get the fairness going down very quickly as we increase block frequency. Block size, same result. It's a bit noisier here, but the trend is clear. Mining power utilization. This is how we secure Bitcoin. I'm measuring here the ratio of blocks that end up in the main chain. Every block outside the main chain is a block that does not contribute to the security of the system. So what's the ratio of these? And we want it to be 1. We want all the blocks to be on the main chain, but when we get forks, we get fewer and fewer of this. Again, this is improving, trying to improve latency. And this is larger blocks. It goes down quickly. Time to win. How long from the time you generate a block until the last competing block is generated? So until any other miner agrees that this is the longest chain and they stop generating competing branches. Maybe bad competitors, but any competing branches. This should be small. We don't want this to happen at all. We want it to be 0 optimally, and we see that as we increase block frequency, we get longer time to wait. As we increase block size, we need longer time to wait until we win as the main chain. So in summary, I talked about scaling the blockchain. We gave clear metrics. This is a way to evaluate results. These experiments did not evaluate any of the suggestions that are currently running on forums and as BIPs. This is just the raw Bitcoin. We wanted to see clear, stark trends. We measure the consensus delay, the fairness, the power utilization, the time to win and the time to prune. These are new metrics that we introduce and we believe are a good way to evaluate alternative protocols. And we introduced the blockchain testbed. We are very happy to run your code on it. We're looking for collaboration here. We want to run experiments. You just need a real working client and it can just work on this node, on this system. We want to make it big, realistic and effective and test real options for Bitcoin and beyond. Speaking of beyond, I would like to present you now Bitcoin NG. Bitcoin NG is a different protocol, a little bit. It's a different and new generation of blockchains, and it solves everything that I presented so far. And the key is as follows. This is tricky. So bear with me. We have 2 types of blocks. We have key blocks. They carry no content. They're just used for leader election. And we have micro blocks. These carry only content, and there is no contention, because only the leader is allowed to generate micro blocks when it is his turn to be leader. So for the epoch until the next key block. So key blocks have the proof of work just the same as Bitcoin, and they have the previous block, which is probably a micro block, just the same as Bitcoin. And they carry a public key K, generated by the miner. Now, every micro block has the actual transactions that this leader wants to introduce, and these are signed with the private key of that leader. So only the leader can generate the private blocks. Now, the interval between the key blocks is the same as Bitcoin or similar. You can have very long intervals here. Say, think 10 minutes. And the micro blocks come in very quickly with short intervals. Think seconds. This can be shorter than the network diameter. Now, fees. Each key block gives the usual subsidy with whatever way you do it. And we need to talk about the fees from the transactions. And the fees are distributed as follows. You have 40% going back to the leader and 60% going forward to the next miner, the next leader. And the reason is essentially this. The next miner, the one that gets the 60, is motivated to place itself as late as possible in the chain. It is motivated to include transactions from the previous miner rather than include them in their own microblock, since they get 60% rather than 40. And the leader on the left, the one that gets the 40%, he's motivated to place transactions in microblocks because then he gets his 40%. Why 40%? Because we have to make some assumptions on the size of an attacker, and we don't want an attacker to be motivated to try to mine multiple blocks and have it becomes complicated. But we can't have this at 10% because then larger miners might be motivated not to place transactions in blocks. You know what? I will go back to double spending later on. If you're interested, I want to present the results now. These are the same experiments we ran before. Now I'm also giving you the results of Bitcoin NG. So we go from left to right. Now Bitcoin NG has 100-second key block intervals in average and 10-second micro block intervals. These are the actual transactions. That's not an average. That's the deterministic interval. And we see that as we increase block frequency, same bandwidth, increase block frequency, we get the consensus delay down, like in Bitcoin, but better. And sorry, this is the consensus delay, yeah. And the same goes as you increase block size. Fairness is where it becomes interesting. Bitcoin NG suffers from no fairness deterioration. Because the key blocks are so far apart, you don't get many more forks. And so the fairness remains about 1. This is qualitatively better. As you increase block size, same. We get it steady at 1. This is some noise, obviously, from the experiments, but it stays at 1. Mining power utilization stays perfect, with some noise, but perfect. Perfect as you increase block size. Time to win, almost no large forks. Same here. It's all great. I talked about 2 things here. I talked about the test bed. In order to evaluate current proposals on Bitcoin, you need clear, explicit, and strong metrics, and you need to run the actual code and emulate the world around it and see what happens. We have our test bed, and we're very happy to collaborate and run more experiments on it with different ideas. I presented Bitcoin NG, different way of running a blockchain. We're very glad to hear your concerns and your comments on this protocol and talk about future adoption in Bitcoin or elsewhere. Thank you very much.
Thank you. That's awesome. Bitcoin NG, Ittay. Nice, nice. All right, we're having a little bit of a switch up.